Assalamualaikum warahmatullahi wabarakatuh. So welcome to our next lecture on heating and cooling load BMFH 3533. So previously we have calculate or we estimate the cooling load based on cooling load sheet figure, and then we are going to the cooling load form, and now we are going to calculate the heat transfer through boundaries. Right. So let's begin. Um, First of all, I would like you guys to ready on your formula and appendix table, uh, and make sure you are print the appendix and formula sheet accordingly, and make sure you are ready with it because we will use the formula and appendix sheet regularly afterwards. Alright, so basically there is some basic design parameter that are usually reflect to our case. For the air temperature and air movement, usually people will feel comfort when we are having 24 to 26 degrees Celsius when summer case. So summer case usually we will refer to us that are in equinox, which is Malaysia. We feel we are more comfort if we reach the temperature 24 to 26 temperature. Less than that or more than that, typically we are having not really comfort, and the winter is 21 to 23 degrees Celsius, and meanwhile the air velocity for summer is less than 0.25 meter per second, and winter is less than 0.15 meter per second. So somehow for the relative humidity for our case for summer is preferable. We are having 40 to 50% of relative humidity. Apart from that, we also feel comfort or comfortable if our indoor air quality, for example, the air contaminants, for example, the particulate matter or dust, volatile organic compound, radon or biofluents, or any gases, pollutant that are dangerous for us is not appear or not exist in that indoor space. And then the ventilation also must be referred to the ASHRAE standard to make sure we receive a very good ventilation rate. Then the cleanliness, for example, the filter that is usually reflect to the air contaminants. Apart from that, we also will feel comfortable if the sound level and the pressure differential between the space and surrounding are in positive. Is this if it is in negative pressure, usually we feel not comfortable. Alright, so this is the recommended noise level for the area. So this is the type of area and the application of area. So usually the recommended noise level is refer to those particular area. So if we want to calculate a design space load, usually it will also refer to the climatic design information. It will influence by the latitude, longitude, altitude, and atmospheric pressure. So usually if you are your location is in the hill or mountain, you are having a very different latitude, longitude, and atmospheric pressure compared to others. Alright, basically there is three mode of heat transfer. Basically there are conduction, convection, and radiation. You can read the typical meaning and how the heat transfer process happen, because I would like not to go deeply on the heat transfer because you are going to learn the heat transfer process, those three mode of heat transfer in your heat transfer subject. So basically for the convection, we have about three types, which is the free convection, forced convection, and also the natural convection. Alright, so this is the formula that we are using to use in this lecture. Basically, we are going to calculate the thermal resistance in feet square hour Fahrenheit over BTU. So basically for the thermal resistance or R is equal to the delta x over k. So the delta x is referred to the thickness. Alright, so and k, wait a minute. So K will be referred to the thermal conductivity. So before I forget, please look into page 2 on your formula and appendix table. We are going to use page 2 until page 7. Page 2 until page 7 we are going regularly to use here. So if you are going to calculate the thermal resistance, if you are going to, you have a thickness, it is given the thickness, so you may use the first formula, which is the R equal to delta X over K. Or you can use, if you the question doesn't give you the thickness or the thermal conductivity, you can either choose the second formula, which is the R is equal to 1 over C. 1 over C. C is referred to the units of conductance. So this is the thermal conductivity here, and here unit of conductance here that we are going to use. So next, after we calculate the thermal resistance, and then we are going to use the formula of overall heat transfer coefficient. So it is BTU feet square hour times Fahrenheit. So U is equal to 1 over sum of R. So you are going to calculate the R, every single R thermal resistance that we have in a question, and then we will sum of it, and then to find the U is equal to 1 over sum of R. So then after we calculate the U, then we are going to calculate the heat transfer rate. So heat transfer rate is equal to Q is equal to U is U. Here overall heat transfer, A is referred to the area, and then times delta T, the difference of the temperature. So the next slide is same to the page 2 until page 7. It just I split it for the building board here, building board is here, and then building papers here, finishing floor material. You can look properly in the table. So let us begin with the question. So now there is the first case study, which is the exercise 1. So as you can see here, there is face brick here, which is the thickness is 4.5 inch, 4.5 inch face brick. So you are going to divide the face brick into 3 parts, which is the first one, which is here is R1, R2, and R3 here. So the formula that we are going to use, either R is equal to delta X over K or 1 over C, since we are going to find the thermal resistance, right? So the R is the delta X over K or 1 over C. So K, delta X we have here is 4.5 inch. So delta X here is 4.5 inch over K. Why we are using the K? Because it's already have the thickness here. You can look into your formula and appendix table here, and then goes into the masonry units. So masonry is referred to the kerja-kerja perbatuan. So masonry units. So we have here brick, face brick. So face brick here, you can see there is face brick here. So the thermal conductivity is 9 here. So there is no C because we already have the thickness here. So you have to make sure when we have the question here, either we choose the C or K. So here is face brick is 9. So R equal to 4.5 inch divided by 9 BTU inch feet square hour F. So the R for this case is 0.5 feet square hour feet BTU. So this is the answer here. So now let's go to the second exercise. So now the case study here is concrete block. So the concrete block here is 8-inch concrete block. So we have to find the thermal resistance also. So R is equal to delta X over K or 1 over C. And then the C is 0.9. How we can get the 0.9 here is because of the thickness. And then just under the brick face there is concrete block. So since this is the concrete block, so it is concrete block here. And then what is the thickness of the concrete block? It is 8 inch. 8 inch here. So the C is 0.9 here, 0.9. So R is equal to 1 over C. We can choose this kind of formula, which is 1 over 0.9. So we get 1 divided by 0.9 here is equal to 1.1 feet square hour Fahrenheit over BTU. So the first exercise and second exercise is simple, and then let's go into the question 3, exercise 3. So now the question wants you to find the overall heat transfer coefficient of U. So remember the formula of overall heat transfer of U is equal to 1 over sum of R. 1 over sum of R. So we have to find the R value first. So how to find the R value? So now the case study have the surface emittance. Surface emittance equal to 0.9. So 0.9 surface emittance is how the surface want to reject the heat. So the emittance of surface emittance is 0.9. And then we have here there is one moving air here going to the face brick with the velocity of 7.5 mile per hour. So next, this is the example of wall from the side view. So this is the outside, and then we have the cement plaster here with the thickness 5 over 8 inch. And then we are going to the face brick here, 4.5 inch face brick with 4.5 inch thickness. And then before going inside, there is also cement plaster here with 5 over 8 inch cement plaster thickness. And then there is still air inside. So you have to divide into several parts of R because you want to find the sum of R here. So the formula of sum of R is equal to R0 plus R1 plus R2 plus R blah 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 until how many thermal resistance of a material that you have. The first one we divide into R0 is here, the moving air, R0 here, and then we have one R1 is here, cement plaster for thermal resistance for cement plaster. Next one is face brick, and then R3 is cement plaster also. Then the R4 is referred to the still air. So